Okay, welcome and thanks for tuning in online. We're going to be talking today about the basics of nuclear weapons. Before we get to that though, I wanted to mention a couple of books for those who want to go into some more detail. First of all, if you really want to understand the physics of nuclear weapons, the Los Alamos Primer is an amazing document. This is the lectures that were given to the scientists as they were arriving at Los Alamos for the Manhattan Project in about 1943. With lots of additional notes and information by the guy who gave the lectures. It really gives you a good introduction to the physics of nuclear weapons as it was understood in 1943 with some updates in the notes. If you want a wonderful page-turner historical account of how nuclear weapons were created in the Manhattan Project, The Making of the Atomic Bomb by Richard Rhodes is really a classic. It's, I think, understandable by everyone, and yet it gets the physics more or less right. If you want a more technical account of the Manhattan Project, Critical Assembly by Hoddeson, Henriksen, Mead, and Westphal is much drier than The Making of the Atomic Bomb, but much more detailed on the technical front. On the effects of nuclear weapons, the US government's textbook on that subject by Gladstone and Dolan is called The Effects of Nuclear Weapons and is still available. And in fact, it's been put online in PDF form if you search for it. And if you want a detailed account of the impact of the bombings of Hiroshima and Nagasaki, there's a book called The Physical, Medical, and Social Effects of the Atomic Bombings that really is a nice job on that. Okay. With that said, let's get started. First of all, just to remind us what we're talking about, this is an image of the Trinity test, the first ever nuclear explosion. It was a huge ball of flame, unlike anything that had been seen on Earth before. So we're going to talk today about how nuclear bombs work, fission, fusion, the different kinds of nuclear bombs. We're going to talk about the nuclear materials that you can use to make nuclear bombs. We're going to talk about what the hard parts are of making a nuclear bomb, and we're going to talk about nuclear weapons effects. Okay, so it all starts with the splitting of atoms. And there are a few large, unwieldy types of atoms. Uranium-235, plutonium-239 are the main ones, that if you hit them with a neutron, will begin to oscillate, and will oscillate with enough energy sometimes that they fall apart into two smaller atoms. They split in half. Okay? And when that happens, the two smaller atoms are not stable with the number of neutrons that the original uranium or plutonium atom had, and so it also releases typically 2 or maybe even 3 neutrons in this reaction. Now, if a big atom has a whole lot of protons, which are positively charged, and neutrons, which have no charge, held together in a big ball in the nucleus, all right? Now, those protons, since they're all positively charged, are all repelling each other. Okay? Like charges repel. Now, what's holding them together is the nuclear forces, the strong and weak nuclear forces, and including those neutrons are like a glue holding that nucleus together. But once it splits, you've got two halves that are each have a lot of positive charge. And so they go flinging apart at extreme speeds, and that's where a lot of the energy that is released in a nuclear reaction comes from, is actually the kinetic energy of motion of those what are called fission products, the products of fission when that atom splits. And you get a lot of energy out of this fission reaction. You get about 200 million electron volts, that's a very rough number, a little bit more for some, a little bit less for others, out of each of these fissions. Now that's more than 1 million times more than you get out of each atom that takes part in a chemical reaction. Why? Chemical reactions only affect the electrons that are in a haze around the nucleus of the atom. They're far away. If this is the nucleus of an atom, then the electrons are way over here someplace and over there someplace. Okay? So they're much more loosely bound. These nuclear forces are much stronger holding that atom together. So when it splits, it releases this huge amount of energy, 10 million times more than the typical chemical reaction as in a conventional explosive. And so that's why you can get so much energy out of one bomb. That's why one bomb from one plane can destroy a city rather than hundreds of planes dropping thousands of bombs, returning again and again and again, as happened to other cities in World War II. Similarly, it can also provide the energy for civilian power generation with a lot of energy coming from a small amount of material in a small space. Just to give you an idea, if you have a 1 gigawatt coal plant, you need an 80-car train full of coal every day to provide fuel. If you have a 1 gigawatt nuclear plant, you need about half of one of those train cars once a year. Huge, huge difference. So almost everything about nuclear weapons and about nuclear power arises from this basic technical fact: you get a lot more energy out of each unit of material taking part in the reaction than you do in the case of conventional things. All right, so, but even though it's a lot of energy per atom, it's still, an atom is very small, and it's still a very small amount of energy. So you need to do gigantic numbers of atoms in order to get a significant amount of energy out of it. So how could that happen? How could you get huge numbers of atoms to split all at once? And the key is this notion that one neutron starts the reaction, one neutron splits an atom, and then that atom splitting releases 2 or maybe even 3 neutrons. And that's what means you can have a chain reaction. You can have the fission of one atom leading to the fission of a couple more atoms, leading to the fission of more atoms, and so on. So here we have an image of fission happening in a group of atoms that's not enough to get that kind of chain reaction going. If it's not enough for a chain reaction to be sustaining, it's called subcritical, less than critical. Critical is when the nuclear reaction can sustain itself over a long time. Supercritical is when it grows exponentially as you want in a nuclear bomb. So here what's happening is a neutron is coming in and hitting an atom, and that releases a couple of neutrons, and one of those neutrons hits an atom, but the other one goes flying out of the group of atoms. And so if that keeps happening, the reaction will come to a halt because you'll run out of neutrons. And you won't have this continuing and accelerating chain reaction. So the question is, if I want to make a nuclear bomb, how do I fix that problem? How do I deal with the fact that my neutrons are leaking out of the system and stopping the reaction? Well, there are really several ways that people have thought of this, how to fix that problem, really 3 ways. So the solution 1 is to add more material. Okay? Here I have a larger group of atoms, and you can see that in most cases the neutrons are hitting other atoms before still some of them fly out into the surrounding countryside, but generally they're hitting other atoms first. And so that will lead to a continuing nuclear chain reaction. So one basic concept that's worth remembering is what's called a critical mass. A critical mass is enough nuclear material to keep this kind of chain reaction going. Okay? Another idea is to reflect the neutrons back in. So here I've pictured the atoms in a box, and the neutron with it is a perfect reflector of neutrons. There isn't any such a thing as a perfect reflector of neutrons. Okay? But there are things that will reflect neutrons more or less well. Generally things that are among the atoms that have a lot of protons and neutrons in their nuclei, the heavy atoms, tend to reflect neutrons better. But some of the lighter things can reflect neutrons some as well. Obviously, if fewer of the neutrons go out because they're being reflected back, you need less material before the reaction can be self-sustaining. So you can reduce the amount needed for a critical mass by having a neutron reflector. Another idea is to take this group of atoms and crush it so that it's more dense. Okay? So the atoms are closer together. If the atoms are closer together, that means that when one of them releases a couple of neutrons, it's much more likely that those neutrons will run into another atom before they leak out of the system. Now these three solutions, enough material, reflecting the neutrons, and crushing the atoms so they're closer together, are often used together rather than just separately. So as you might imagine, what you want ideally is for if you want to have a critical mass with the least amount of material, and the material is expensive to produce and difficult to produce, as we'll talk about, so you do want to use as little material as you can. And so usually having it in a sphere is a good idea, because if it's in a flat pancake, then there's lots of opportunities for the neutrons to leak out. If it's in a sphere, it's the minimum surface area for those neutrons to come out of. So you will often see in describing particular kinds of nuclear material a phrase that's the bare sphere critical mass. So that's how much you need to have a critical mass if it's in a sphere and if the sphere hasn't got any neutron reflector around it, if it's bare. Okay? So remember the idea of a bare sphere critical mass. Okay, now, what's going to happen when this chain reaction starts happening? What happens is this energy is getting released, and it gets released incredibly fast. These reactions take place in times measured in billionths of a second. In fact, during the Manhattan Project, the scientists invented a new time unit, a shake. You know, the expression 2 shakes of a lamb's tail, referring to some very short period of time. A shake is 10 billionths of a second. And that's sort of the time frame for fission. Okay? So what happens is it's releasing all this energy in a pretty small ball of material. And that means that material is going to heat up, it's going to turn to gas, and it's going to start blowing itself apart. Well, if bringing the atoms closer together by crushing them and increasing their density reduces the amount you need for a critical mass, having them expand out increases the amount, and it causes the neutrons to start flying out into the surrounding countryside again, and it shuts down the chain reaction. So the key difficult part of making a nuclear bomb is figuring out, how do I get my material together into the shape that I want it to be in to get a good explosive yield out of it before it starts blowing itself apart. Because one of the key things to understand about these materials is that sometimes they fission by themselves, what's called spontaneous fission, and they release neutrons. So there are always some neutrons around. So you can't just have your nuclear material sitting in a supercritical form because it's going to start going off. So the key problem is, how do I get the material together into the form I want it in, a form that's really supercritical, that's way beyond what's needed for just a self-sustaining chain reaction, will give me a growing, explosively growing chain reaction before it starts blowing itself apart. Okay, that's the key problem, getting the material together fast enough. All right, so there are two ways people have thought of to do this, basically. One is what's called a gun-type bomb. And that is literally slamming two pieces of nuclear material together at high speed. Now, if I had, for example, 2/3 of a critical mass of highly enriched uranium in this hand, let's pretend I'm strong, because that would be quite a bit of material, and 2/3 of a critical mass of highly enriched uranium in this hand, and I brought them together with my hands as fast as I can bring them together with my hands, that would not give me a good nuclear bomb. Why? Because as they got maybe somewhere around here, they would be close enough together that together they would be a critical mass, and as soon as a loose neutron started a reaction going, it would start going. And that uranium would melt and turn to gas, and it would blow itself apart before I got any significant nuclear yield out of it. Everybody in this room would be dead. I'd certainly be dead. We'd have a tragic accident, but we wouldn't have many blocks of a city vaporized in a nuclear blast. So the way that a gun-type bomb works is to slam those pieces together much faster than I could do it with my hands. The bomb that obliterated the Japanese city of Hiroshima was literally a cannon that fired one piece of highly enriched uranium into another piece of highly enriched uranium. So these are simple and reliable types of nuclear weapons. The United States never bothered to test the Hiroshima bomb before using it because it was so obvious it would work. And the basic idea of the Hiroshima bomb was worked out by one professor and two of his graduate students in the summer before they all arrived at Los Alamos. So this is not an incredibly complicated thing, unfortunately. With a gun-type bomb, you can only get a good yield with highly enriched uranium. You can't get a good yield with the other nuclear material we'll talk about, which is plutonium. Why? Because plutonium falls apart much more than highly enriched uranium does. So there are a huge number of neutrons flying around when you have plutonium, even if you have quite good plutonium. And therefore, as the two pieces are coming together in a gun-type bomb, even fired from a cannon, they'll start fissioning before they come together in the full configuration that you want. So you won't get a Hiroshima-scale nuclear bomb trying to do a gun-type bomb with plutonium. So you can only get high yield with highly enriched uranium. Okay? So if what you have is plutonium, or if what you have is not enough highly enriched uranium for a gun-type bomb, because remember, those gun-type bombs are very inefficient, then what you use is an implosion-type bomb. So this is one where you are trying to crush that nuclear material down to a higher density. These are much more efficient and therefore need less nuclear material. Just as to give you some ballpark numbers, the Hiroshima bomb, which was the inefficient gun-type bomb, had about a little over 60 kilograms of 80% enriched material in it. That it means 80% of the material was uranium-235 as opposed to uranium-238, which has 3 more neutrons in it, which is the other kind of uranium that is in the uranium you dig up out of the ground. We'll talk next time about how you produce highly enriched uranium and plutonium, and we'll talk a little bit more about the different kinds of elements which are called isotopes, which are things that have different numbers of neutrons in the nucleus. An element is defined by the number of protons it has in the nucleus, and the isotope of an element, like uranium-235 or uranium-238, is those numbers, 235, 238, are the number of protons plus neutrons in the atom. Okay, so back to the implosion-type bomb. So here we have a picture that shows the nuclear material surrounded with some other stuff that I'll talk about in a moment, and then surrounded by explosives. And a lot of the explosives are cut away here so that you can see what the assembly looks like. All right? Now, what you need to do in this situation is you need to detonate the explosives at exactly the same time all around this bomb, because if the explosives on this side go off first, before the explosives on the sides go off, what you'll have is not a crushed ball, but a pancake. And remember, in a pancake, the neutrons are leaking out all over the place. Okay? So what you want is a crushed ball, which means you need the explosive shock wave to be a spherical shock wave going inward. All right? So that's significantly more complex to design and build, and would be much more difficult for terrorists, although still conceivable, especially if they got knowledgeable help. And there are some approaches that are significantly less complex than the Nagasaki bomb was. I can't say much more than that in this unclassified talk. So most of the approaches require explosive lenses. They require millisecond timing of multiple detonations. It is a tricky thing. But as I say, there are some approaches that are less complex. Okay, let me talk a little bit about the evolution of designs for implosion bombs, because they have changed over the years. Okay, so the Nagasaki bomb was a solid ball of nuclear material. Okay? Nagasaki bomb was about, unlike the Hiroshima bomb that was about 60 kilograms of highly enriched uranium, Nagasaki bomb was about 6 kilograms of plutonium. Now, plutonium is about 3 times more reactive than highly enriched uranium. So even if they were identical bombs, you would have needed 3 times less plutonium. The reason you needed 10 times less is because you had the implosion device rather than the gun-type device, and the implosion is much more efficient. So you have this solid ball of about 6 kilograms of material, a ball that fits in my hand. I'll show you a picture in a minute. And around that, you had some heavy stuff for what's called tamper. So the tamper does 2 things. First of all, it's the neutron reflector, reflecting those neutrons back in, the way I talked about before. But secondly, if you think about it, you would like to figure out a way to keep that material from blowing itself apart for at least a little bit longer. And if you think about it, even a tiny amount of time might help a lot. Why? Because in one of these exponentially growing chain reactions, let's say it was doubling every neutron generation. So an atom splits, releases 2 neutrons, each of those split 2 more atoms, releases 2 more, and so on. Then the last neutron generation, in that case, would be giving you a big chunk of all the energy you were getting. So if you can keep it from blowing itself apart long enough for just 1 or 2 more generations of neutrons to happen, you can get a substantial amount of yield. Now, so one idea would be, let's put a steel cage around the thing, hold it in. Turns out there's no way you can hold this in. You've got a ball that is roughly this size, where as much energy as 10 or 20,000 tons of conventional explosives has just been released. Okay? And the ball has turned to gas, and that gas is at unbelievable temperature and pressure. Billions of degrees, incredible pressure. Okay? And that ball is going to go flying out no matter what you do about it. Okay? There is no steel cage or whatever material, titanium, whatever, that's going to hold that ball from blowing apart. But if you just have something heavy around it, then the inertia, it has to move that heavy stuff in order to blow out. And that might slow it down. Again, we're talking about billionths of seconds here. It might slow it down enough to give you enough extra growth in the neutron population to have a significant amount of extra energy release. So pretty much every nuclear bomb you're going to see is going to have this stuff, the tamper, around it. Okay? And then around that, you would have the conventional explosives, okay, in these explosive lenses. All right. Now, so things have evolved since that first generation thing. And one thing people thought of is, let's not have a solid ball. Let's have a hollow ball. Okay? Hollow ball of nuclear material. Why? Because when the explosives crush it, it starts off, since this part is nowhere near that part, it starts off quite far from being a critical mass. When the explosives crush it, it doesn't become a critical mass until it's all crushed down in the middle. Okay? And it's much easier for the explosives to crush it at high speed because there's this big empty gap in the middle. Okay? All right, so that was step one in the evolution. Another good step in the evolution was creating an air gap in between the explosives and the ball in the middle. You still got tamper, but you have an air gap between the explosives and the ball. This is sometimes referred to as a levitated pit. This ball of nuclear material in the middle is called the pit of a nuclear weapon. Now, why would you want an air gap? All right, think about this. When you're pounding on a nail, would you want to have the hammer right in contact with the top of the nail and just press on the nail? No, you're going to get almost nowhere with that. What you want to do is pull the hammer way back and whang that nail. Give the hammer enough time to accelerate before it hits the nail. So here the explosives accelerate through the air gap before they hit the nuclear material. And it turns out it crushes the ball much more efficiently if you do that. Okay? Now, then came the really big evolution. Okay, so we had hollow balls, we had levitated balls. Okay, now we're going to put something else in the ball. Okay? Put a little tube in the ball, and you put some tritium. It's a hydrogen atom with 2 neutrons and a proton. Okay? Referred to as tritium. If it has only 1 neutron with the proton, it's referred to as deuterium. Okay? So, what happens is, when the fission reaction goes, and you have this tiny ball heated up to billions of degrees, okay, that will cause a fusion reaction in this tritium. Okay? And that fusion reaction will do 2 things. It will release a bunch of energy itself, and it will release a bunch of really fast neutrons that will fission more of the nuclear material. Okay? So you get, this is what's called a boosted weapon. This is not yet a real hydrogen bomb, but it's what's called a boosted weapon. The fission is being boosted by the fusion. Okay? So every modern thermonuclear weapon in the US nuclear arsenal, in the Russian nuclear arsenal, is a boosted weapon like that. Okay? All right, now, I apologize in advance. Now we're going to get really complicated for a minute because we're going to talk about modern thermonuclear weapons. And, you know, nuclear weapons designers have been creative over the years and things have gotten complicated. But let me just try to go through it for a minute here. All right, so you start off with the primary, also known as the pit. Okay, that's the same thing we were just talking about. So that's a hollow shell of nuclear material. It's got some tritium inside it. Okay, so the explosives go off. They crush that ball. The fission reaction starts going. You also have what's called a neutron generator in the middle of that ball that set off a shower of neutrons at the right moment so that your nuclear reaction goes at the time that you want it to. Okay, so your fission reaction goes off. It starts some fusion with the tritium that's in the middle of the pit. okay? The tritium causes some more fission to happen. So fission causes fusion, then fusion causes more fission. Okay, so then you have a huge amount of energy released by that pit. That energy is focused on what's called the secondary. The secondary will have lithium deuteride, typically. So that is the fusion fuel. The deuteride means it's got deuterium, which is in a chemical bond with this lithium. The lithium actually splits from all this energy and provides tritium that the deuterium can fuse with. Okay? So you have this energy from the fission and fusion of the boosted pit that is then focused on the secondary, and it actually crushes the secondary with radiation pressure. Believe it or not, it's the pressure of very high frequency light, gamma rays, X-rays, that actually is like a hammer crushing the secondary and heating it up. So you have these incredible pressures and temperatures in the secondary that then lead to fusion in the secondary, which releases a huge amount of energy and also releases a big shower of neutrons. And so the designers thought, well, if we got another big shower of neutrons, let's put in some nuclear material and have some more fission as a result of those neutrons. So what you have, now this just stay with me for a minute. You have fission that starts the whole thing, fusion that boosts that fission more. All of that then causes fusion, which then causes more fission. So you have a fission, fusion, fission, fusion, fission reaction. In the end, you end up with a typical bomb you might have of order half of the energy coming from fusion, half coming from fission. The designer can change those proportions considerably. Nobody has ever managed to come up with a fusion bomb that doesn't have a fission bomb to set it off. Okay. Now, most of the nasty radioactive fission products that create fallout and things like that are coming from the fission. They're coming from the splitting of uranium or plutonium. So the fusion part is, in a certain sense, a cleaner bomb than the other part, which is why people thought, gee, couldn't we figure out how to make a fusion bomb without the fission part? Nobody's ever figured out how to do that. Okay? All right, onward. So to make nuclear bombs, there are basically two key potential bomb materials. Next time we'll talk more about how to make these. The first is highly enriched uranium. All right? When you dig uranium up out of the ground, less than 1% of it is the kind that's easy to split, uranium-235. 0.7% is uranium-235, and 99.3% roughly is uranium-238. Uranium-238 is almost useless for fission. It will split under certain circumstances, but it can't sustain a fission chain reaction. So you got to separate those. You got to figure out, how do I get from 0.7% up to very high concentrations of uranium-235? Almost all, and that process is called enrichment. The more U-235 percentage you have in your uranium, the more enriched the uranium is. So when people say highly enriched, they mean 20% or more uranium-235. That's the international definition of highly enriched uranium. And almost all the techniques that people have thought of for how do I get those U-235 atoms separate from the U-238 atoms have to do with the very slight difference in mass. So the mass basically goes as the number of protons and neutrons in the nucleus. So it's 238 rather than 235. So it's only a little more than 1% difference in the mass, and that slight difference is what most of the approaches play on. And we'll talk about a couple of the approaches that have been next time. But There's gaseous diffusion approaches that use huge amounts of energy. There's centrifuges. There's a variety of others. Okay. Plutonium is what they figured out to do with the uranium-238. If you put uranium into a reactor, and there's instead of an explosively growing chain reaction like in a bomb, you have a steady state chain reaction, you still have neutrons all over the place. Okay? And some of those neutrons, when they hit uranium-238 atoms, they get absorbed. And so you have uranium-239. But uranium-239 isn't stable, and it kicks out some things and decays to plutonium-239. Okay? And plutonium-239, it turns out, is a nice weapons material the way uranium-235 is. And so you can take this useless uranium-238 and turn it into plutonium-239. You only end up with something like 1% plutonium in the spent fuel from a reactor. And so you have to chemically separate out the plutonium that you want from all of the other stuff. The remaining uranium, the fission products, which are intensely radioactive and nasty, you want to get the purified plutonium. And that chemical process of separating out the plutonium is called reprocessing. Okay? And we'll talk about that more next time. There are a few other isotopes that have this property that they are big and unwieldy enough that when a neutron hits them, they'll split and they'll release more than one neutron so you can have a chain reaction. But there aren't any others that have ever been used for stockpiled nuclear weapons in a state. Now, the key point is none of these materials occur in nature. There isn't a rock you can turn over that will have highly enriched uranium in the rock or plutonium in the rock. All of them are extraordinarily difficult to produce. So in a certain sense, Mother Nature has been both kind and cruel to us in the way she set up the laws of nuclear physics. Kind in the sense that these materials don't exist in nature and they're hard to produce. And so our species didn't invent them until we had developed civilization to a reasonably extensive degree. But cruel in that once you have these materials, it's actually not as hard to make a nuclear bomb as it would be preferable for it to be. Now, as I mentioned, the amounts of material required are not very big. So this hand has a glass ball, not a plutonium ball, that is the same size as the ball for the Nagasaki bomb. So that is just not a big amount of material. For the gun-type bomb, you need more, as I mentioned. But the amount that you have, because uranium is very dense metal, would fit roughly in two 2-liter bottles. Okay? And again, as I mentioned, it's only 6 kilograms for Nagasaki, of order 60 at Hiroshima because of the greater efficiency of the implosion bomb. What's more, it's not particularly hard to smuggle this material. This is a guy by the name of Sergeant Herb Blair. He's carrying in one hand a box that has the plutonium core for the Trinity nuclear test, the first ever nuclear bomb. You can see he's got no special equipment. He's wearing a t-shirt and remarkably dirty chinos. And he's carrying it in one hand. So once nuclear material gets out of the place where it's supposed to be, if it's stolen or something like that, it could be anywhere. And trying to find it and recover it is a very difficult job. It is radioactive. Any material that you can make a nuclear bomb out of is an atom that is unstable and therefore is radioactive. And you can detect that radioactivity. But turns out highly enriched uranium especially, and also to a lesser degree plutonium, are not so radioactive that either they require special equipment to carry them around or to make them very easy to detect. Years ago, I was talking to a guy who had done a sort of international survey of the radiation detection equipment that was available for people to install at borders and so on. And one of the things you'll see at airports and things like that that are international, you'll often see that the customs guy is wearing a little pager on his belt. Well, that's a radiation detector. So I said to this guy who'd done this survey of the equipment, let's suppose I'm a customs guy. I've got one of those things on my belt. The bag directly in front of me that I'm looking at has enough highly enriched uranium for a bomb in it. What is the probability that that detector will go off? He said 0. Okay? Now, the bigger detectors, that's not true. The bigger detectors have some chance of detecting highly enriched uranium, but it's relatively easy to shield. Some of the radiation it emits is similar to things that normal radioactivity. You'd be surprised how much radioactivity is just around us in nature. You get a certain radiation dose when you eat a banana, for example. And kitty litter is one of the things that routinely sets off radiation detectors at borders. Detection is another issue, but it's just not that hard to smuggle nuclear material, is the point I'm trying to make. All right, so some somewhat misleading terms that you should nonetheless remember. First of all, highly enriched uranium, I mentioned that's 20% or more uranium-235. Natural uranium is what you dig up out of the ground, that's 0.7% uranium-235. Low enriched uranium is when it has more than 0.7% but less than 20%. Typically for a power reactor, you're talking somewhere in the range of 4 to 5% uranium-235. Depleted uranium is what you get when you've stripped out some of that U-235 to make highly enriched uranium or to make low enriched uranium, and then the waste that you've got that's almost all uranium-238 is what's called depleted uranium. So it has less than 0.7% U-235. Now, here's where things get misleading. Weapon-grade uranium is typically, it's a little bit different in different countries, but it's typically uranium, certainly with 90% or more. In the United States, it's officially 93% or more uranium-235. But bombs can be made with material that is much less than weapon grade. It's an irony of history that the Hiroshima bomb, the first ever nuclear weapon used in war, was not made out of weapon grade material. It was made out of 80% enriched, highly enriched uranium. All right, so similarly, weapons grade plutonium, again, a little bit different depending on where you are, but typically sort of 93% or more plutonium-239, which is the isotope you want. Why is plutonium-239 the isotope you want? It turns out if the material absorbs one more neutron, then it turns into plutonium-240. And plutonium-240 has a huge spontaneous fission rate. It falls apart and releases neutrons all the time. And so you end up with lots of neutrons flying around if you have a lot of plutonium-240, and makes it more difficult to make your nuclear bomb. Plutonium-238, which is produced in a somewhat more complicated way, but comes up a little bit as you irradiate the uranium longer and longer, generates a huge amount of heat. Plutonium-241 isn't as bad as 240 or 238, but it's still not great, and so on. So plutonium-239 is the thing that, if you're a bomb designer, you prefer to have. So in a power reactor, what you do is you leave the uranium the uranium fuel in the reactor for a long time in order to efficiently produce power. In a plutonium production reactor for weapons, you leave the material in for a relatively short time in order to maximize the plutonium-239 and minimize the degree to which it absorbs more neutrons to build up these undesirable isotopes of plutonium. So the stuff you get out from a power reactor is referred to as reactor-grade plutonium. It has much less plutonium-239, maybe only 60% or 70% plutonium-239. And weapon makers much prefer the weapon-grade plutonium. But just as with the uranium, it is possible to make reliable, effective nuclear weapons from reactor-grade plutonium once that plutonium has been separated out from the spent fuel by this process known as reprocessing. So this is just more on the point that you can make bombs with reactor-grade plutonium. It has a higher neutron emission rate, it has higher heat emission, has higher radiation. All of those can be addressed by bomb designers. And this is just a long disquisition on that topic, officially from the US government. This is, again, going back to the point that highly enriched uranium well below weapon grade is weapons usable. This is how much material you need if you do have a neutron reflector around a sphere as a function of what percentage of uranium-235 it is. And what I want you to see is that the graph is pretty flat for a long time until you get down to sort of 50, 60% uranium-235, and that's when it really starts going up. Now, as I mentioned, there are other isotopes that could conceivably be used in nuclear explosives. They're very difficult to produce and separate out. Only a couple of countries have kilogram quantities of separated materials of these other isotopes. So I include them only for completeness. All right, so what are the hard parts of making a nuclear bomb? First, making the nuclear material. That's overwhelmingly the most difficult part. More than 90% of the effort in the Manhattan Project was devoted to making the nuclear material rather than to the design, the manufacturing, etc. of the bomb. In fact, in the Manhattan Project, as I'll talk a little bit about next time, they built in just a few years an industrial floor space that was bigger than the entire US automobile industry that existed at that time. They were using, I think, something like 5 or 10% of all of the electricity generated in the United States for enriching uranium. It was a gigantic industrial enterprise to make that weapons-usable nuclear material. All right, second hard part is if you want to make the kind of bomb that a state would want to have, something that's efficient, that's safe, that's reliable, that's predictable, that you can put on a combat aircraft or better yet on a ballistic missile. It is far harder to make that kind of a bomb than it is to make a terrorist nuclear bomb that would be crude, unreliable, maybe put in the back of a truck. Unfortunately, that's much, much easier to do if you have the nuclear material. So that's why security for nuclear material is important enough to keep it out of terrorist hands, to be the subject of these global nuclear security summits that have been taking place since 2010. All right, the third really hard part is designing and making a hydrogen bomb. That complex thermonuclear weapon I talked about, thermonuclear, hydrogen, fusion, all of those are referring to the same thing. That is extremely complex and I think very difficult to do without some degree of testing. There is no central secret to making nuclear weapons, but there are a variety of very real engineering and manufacturing challenges. All right, so suppose I'm a terrorist group and I have dramatically less resources than a state has. I don't have anything like the money that a state has. I don't have anything like the organizational capacity that a state has. I don't have anything like the technical expertise that a state has. How am I going to put together even a crude nuclear bomb? So the first hard part, again, getting hold of the nuclear material. Once they have that, there is unfortunately a significant risk that they might be able to make a crude nuclear bomb. And that's been the conclusion of repeated studies by governments, not only in the United States, but in a number of countries elsewhere around the world. So even once they have the nuclear material, though, it remains somewhat difficult. It would be, I think, the most technically challenging attack that any terrorist group has ever accomplished, if it happened. They have to process the material into an appropriate form. So they might get, instead of metal, they might get, for example, research reactor fuel that's typically a mix of aluminum and uranium. And they'd have to actually chemically separate out the uranium from the aluminum, and then they'd have to convert it to metal. Okay, so some degree of chemical processing may well be required depending on the kind of material that they manage to get hold of. Now, on the other hand, and you might say, well, terrorists couldn't do that, but then it turns out that the there's a lot of things that we know terrorists and other adversaries do routinely that involve a fair amount of chemical processing. Going from a poppy plant to heroin actually involves a substantial and fairly sophisticated set of chemical processing. All right, casting and machining. Once you have the metal, you have to cast it into the right shape for the components of your bomb. Then you have to machine it to make sure it's exactly the right shape. You have to build your explosives, the reflector, etc., and get them to work. If you wanted to do an implosion weapon of the standard type, then you'd have to have precisely shaped explosives with very precise timing and so on. That'd be really quite difficult. And all that requires you to be able to recruit skilled people, raise money, and sustain an organizational effort over a substantial period of time, which is something terrorist groups in most cases are not good at. So some scenarios might allow you to bypass some of these steps. Just to give you an idea, in the US Department of Energy, there are some facilities where the security rules require them to have a security plan that prevents the terrorists even from getting to the nuclear material, let alone leaving the building with the nuclear material, because of concern that terrorists might be able to set off a nuclear blast while they're still in the building, if they manage to get there. I won't say any more than that on that topic. So here are a few technologies you might want to remember because they're sometimes in the news. Krytrons. These are devices for delivering a very powerful electrical signal, a big spark, with very precise timing. And they do have civilian applications. They're used, for example, in lithotripsy for smashing kidney stones, a subject dear to my heart since I've had kidney stones multiple times. But they're used for detonating explosives in implosion systems. There are various alternative approaches that can also be used for detonating the explosives. Neutron generators. This is another one of the hard parts. It's tricky to get. You want a shower of neutrons set off at exactly the right moment, but it's a moment when the conventional explosion is already crushing down the nuclear material. So figuring out how to make something that's going to generate the neutrons you want right at the right moment in the right way and not send off a whole bunch of neutrons ahead of time is a little bit tricky. It's not necessarily required for gun-type bombs because they can rely on stray neutrons that are always around. But it's needed for implosion-type bombs. X-ray flash photography is another thing that's often used, especially in state programs, because you want to be able to take a sort of strobe picture of the imploding system to see if it's imploding properly. All of these things are subject to export controls. They all also have civilian uses. All right, let's talk for a minute about the effects of nuclear weapons. And just to give you an idea, this is what Nagasaki looked like a month after the bomb was dropped. You can see it's an image of almost total devastation and destruction. So the first thing that happens is the nuclear fireball. All right, so back to our ball of nuclear material. So in less than a millionth of a second, we have released the equivalent of, say, 15,000 tons of chemical explosives in a ball this big. The ball hasn't had a chance to expand yet. So that energy is all contained in this tiny little space. So we're talking literally billions of degrees, much hotter than the center of the sun in the center of this ball, okay? And unbelievable pressures, okay? So that ball is going to be radiating like mad. It's going to be sending out gamma rays, X-rays, etc., because of that incredible temperature and pressure. And that pressure will cause it to fly outward. So that ball will grow at incredible pace, sending out these gamma rays, X-rays, etc. And as it gets bigger and at least slightly cooler, it will still be a fireball, but it will be sending out visible light, infrared light, and so on. So this is an image of the fireball from the Trinity nuclear test. You can see this one was set off in a tower a little bit above the ground, but the fireball was big enough that it came into contact with the ground, and in fact melted. You can still go and visit the site. It melted the sand and rock underneath, and you can go to that site and pick up little pieces of what's called trinitite, which is the sort of molten glass that resulted from that. A friend of mine actually took a piece of trinitite into the lab and managed to detect the presence of an isotope created when the barium in the explosives absorbed neutrons from the ongoing reaction. And so decades later, just from a piece of stuff picked up out of the ground, he was able to confirm that barium was used in the explosives of the Trinity test, which is in fact true. All right, so at the edge of this expanding thing, there's incredible pressure still at the sort of outer edge as it's moving out. That's called the shock front. And that's labeled here. And you can see there's sort of a dirt cloud coming out as it kicks up dirt. All right, so this fireball is hot, right? And in the middle, it no longer has high pressure. So what happens with really hot air is it rises. So the fireball, incredibly hot, the blast is going out like this. The fireball is starting to rise because it's hot, and it's starting to spread, and it's sucking up air that's coming up into this column, okay, because it's lifting up, and so in order to avoid creating a vacuum underneath where it was, air comes in from the sides and comes up in this column, and then it's going out, and it creates the classic mushroom cloud. Okay? All right, so the question is, how far do various effects occur? And the answer depends on how big your bomb is, as you might expect. One of the surprising things is that the different effects scale differently with the size of the bomb. Some of them scale roughly by the 1/3 power, like the blast of the bomb scales roughly by the 1/3 power. Some of them scale by the 0.4 power roughly, the radius at which the thermal effects will be enough to set things on fire or to cause third-degree burns or what have you. Scales as roughly the 0.4 power, but the radiation radius scales at a much smaller number. So that means that for small bombs, the radiation is more important than it is for big bombs. For big bombs, other things become more important, as you see here. So the prompt radiation in the case of a 1 kiloton bomb, a small nuclear bomb, actually extends further as a potentially lethal effect than any of the other effects. Whereas for a 100 kiloton bomb, it's the thermal that extends the farthest, and even the blast extends further than the prompt radiation. So I should say there are really two kinds of radiation from a nuclear blast. One is what's called the prompt radiation. So you have, as I mentioned, gamma rays, X-rays released essentially instantly, and you have neutrons that are released essentially instantly. But then you also have the delayed radiation. That's coming mainly from the fission products from fission, which are extremely radioactive. And what happens, especially if there are two ways you can detonate a bomb. You can detonate it up in the air, which turns out to be best for creating a big blast over a wide area, or you can detonate it right on the ground, which is called a ground burst. That's best if you want to destroy hardened things right near where that blast is, like an underground missile silo or an underground command bunker or something like that. Either on the ground or close to the ground is best for that purpose. But if you're on the ground or close to the ground, what happens is the fireball comes in contact with the ground, it vaporizes a whole bunch of rock, sand, whatever's on the ground there, and that stuff gets sucked up into the mushroom cloud. It mixes with those nasty fission products, those really radioactive fission products, while it's in the mushroom cloud, and then it starts falling down downwind from the reaction. That's what's called fallout. Okay? So if you have an airburst to maximize the area that you're destroying buildings over, you don't have fallout. There, the fission products go way up into the upper atmosphere, disperse over the whole Earth. You don't have stuff raining down just downwind of the blast. But if you have it close enough to the ground so that it comes in contact, the fireball comes in contact with rock, dust, etc., and sucks it up into the cloud, then you're going to have fallout. Okay. So this here is only referring to the prompt radiation, the neutrons and the gamma rays and so on. So the fireball, there's the blast. Let me talk about the blast for a little bit. The blast is basically a big shock wave like you would have from a conventional bomb, only it's much bigger over a much broader area. With the combination of effects, it is usually thought that most people that are in the area, if it's a fairly large bomb, like a 10, 20, 30 kilotons and up, most people who are in the area that has at least 5 pounds per square inch of blast pressure, what's called overpressure, will probably die. Most of the people who are outside the 5 psi radius will probably live. Now, that's a very rough, very, very rough approximation, and there are much more detailed models and effects calculators and so on. But there are calculations that have been done over the years that use what's called a cookie cutter model, where they just assume everybody dies within 5 psi and nobody dies outside 5 psi. And the mistake you make by assuming everybody dies within 5 psi is similar in size to the mistake you make by assuming everybody survives outside the 5 psi. And so, but it is a gross oversimplification. It doesn't really work if the population isn't sort of homogeneous over a broad area and so on. So this just gives you the areas that go along with those effects. So this is a somewhat more detailed calculation about who would die. So this is where the overpressure is greater than 12 psi. Then almost everybody dies. In the 5 to 12 psi range, of order half the people die, and almost everybody is seriously injured in some way. Then you have, in the outer ranges, you have some people dying, substantial number of people getting injured. As you get out toward 1 to 2 psi, you have a minority of people who are injured. So what kinds of injuries are we talking about? So first of all, from the blast, what usually happens is people being crushed, buildings falling down, etc. From the heat, we're talking about people being burned. From the prompt radiation, we're talking about radiation sickness that might take you a couple of weeks to kill you. That is, if the dose is big enough to kill you. So we're talking about, in the case of both Hiroshima and Nagasaki, tens of thousands of people being really horribly killed, and tens of thousands more being really terribly, terribly injured. So what we've talked about today is the basics of nuclear weapons. Some takeaway points. You need highly enriched uranium or plutonium to make a nuclear bomb. Those are hard to make. The amount of material you need, however, is small. The hardest part of making a nuclear bomb is making the nuclear material. There are other difficult parts, however. And the effects are overwhelming. A single nuclear bomb can incinerate the heart of a major city. So, next time we will talk about how is it that you make plutonium and highly enriched uranium. Thanks again for tuning in.